welcome back to this session. So from today's session onwards, we will be starting the last unit of this subject, this course, Mechanics of Structure. Okay, and the last unit is unit number 6, and this unit is all about columns. So what is a column? So column is any structural member which carries a axial compressive load. Okay, if it carries a axial compressive load, this type of structural member is called as a column, and this column will most of the time will be under compression. Okay, it will be under compression. क्यों compression पे होंगे? क्योंकि ये कॉलम जब ऐसे वर्टिकली, व्हेन इट इज स्टैंडिंग वर्टिकली, इसके ऊपर, इसके नीचे यहाँ पर फ्लोर है, तो इसके ऊपर से एक और फ्लोर आएंगे, which you can call a slab. One more slab will be coming from the top. So this column will be sandwiched between the two slabs. Okay, so जब कॉलम ऐसे दो slabs के अंदर sandwich होते हैं, तो the column will be under compression. Okay, and these columns are compression members. So let us see some of the terms that we will be using again and again in this unit. So the first one is buckling. Okay, now what does buckling mean? As you can see in this diagram here, buckled steel column here, buckled RCC column. So from the figure here, you can clearly see that the column which is taking a compression, which is under compression, has bent. It has bent, right? यहाँ पर भी bending हुआ है, यहाँ पर भी bending हुआ है. So buckling is nothing but the bending action of a column is called as buckling or crippling. इसको buckling भी बोलते हैं और इसको crippling भी बोलते हैं. Okay? The buckling of the column depends on its initial curvature, column end conditions, and eccentricity of loading. तो ये buckling किसके वजह से आते हैं? It depends upon three main factors. One is initial curvature, then column end conditions, and eccentricity. Now for this column end condition, अगर if the column which is carrying a load from above, अगर उस ऊपर के लोड कम है तो इसका बकलिंग ज्यादा नहीं होगा, right? अगर the load that it is carrying at the top, if it is very heavy and the column sections given are very not adequate to take the load which is coming from above, then the column will again buckle, right? And it also depends upon the eccentricity of loading, where the load is acting. Okay, eccentric load, I hope you remember it. Eccentric loads are those loads which acts away from the neutral axis. Okay, so I hope this buckling is clear. Now next, radius of gyration. This radius of gyration is also used time and again. This we have already come across this term from chapter number 1 only, unit number 1 only. So what is radius of gyration? It is a property of a section and it is denoted by K. Okay, mostly it is denoted by K. So from the relation moment of inertia I equals to AK square, we get K square equals to I by A, and K will be equal to root over of I by A. This you should know it because we have already come across this term, and we have also calculated radius of gyration for various sections, right? So here K is radius of gyration, I is moment of inertia, A is the area of the cross section. Now if you have to find radius of gyration for a solid circular column of diameter D, अगर आपको solid circular section के radius of gyration find करना है, तो there K is, since K square, using this relation here, K square equals to I by A, the moment of inertia of this solid circular section will be pi by 64 d raised to power 4. This will be the moment of inertia. Area of this circular section will be pi by 4 d square. Now putting this in this manner here, you'll get this k square. यही formula पे लगा रहे हैं. So you'll get k square equals to pi by 64, which is this one is I and a. So if you cancel it, you will finally get d square by 16. Okay. Now दोनों की side पे square square है. So if you remove this square here, and this will be under root here. Okay. Now after removing this root, d square यहाँ पर d square अगर आपने d square को root से बाहर निकाला तो it will be d only. And square root of 16 will be 4. So k will be equal to d by 4. Okay. So this is the radius of gyration for a solid circular section. Now here, similarly, for a hollow circular section, or for a hollow circular column, k radius of gyration जैसे हमने आगे solid circular section के लिए फाइंड किया था वैसे I by I दोनों ही निकलना पड़ेगा. After that cancelling, you will get k equals to root over of d square plus d by 4. So this is the one that we will be using. Okay. And similarly now here it says the buckling of column takes place about the axis having least strength, that is least moment of inertia. जहां पर least moment of inertia आते हैं वहां से column का buckling होना शुरू होते हैं. Okay. Hence in column problems we shall always consider least moment of inertia. So हम जब भी column के problems करते हैं वहां पर हम least moment of inertia लेते हैं, which are Ixx and Iyy. Along this Ixx and Iyy minimum जो है हम वो लेके जाएंगे. Okay. Hence we have to consider minimum radius of gyration. तो radius of gyration भी जो हम consider करते हैं वो भी हमें minimum consider करना पड़ेगा. Okay. So the formula for radius of gyration will hence be k minimum equals to I minimum by a. Okay. So I hope this is clear. Now in Euler's formula mostly we require the value of k square. अब जब हम Euler's formula आगे जाके हमें Euler's formula use करना पड़ेगा. So instead of k equals to d square root over of d square plus d square by 4, ये use नहीं होगा. We will not be using this formula a lot क्योंकि Euler's formula पे k square का value given है तो we will be using this one here. Okay. जहाँ पर k square आया है. So यहाँ पर last पे आपका value k square पे आया है. So we will be using this value mostly. So here we will use k square, this value here. And last पे जो हमने solid circular पे मिला था इसका value will be this one. Okay. So now what is effective length of a column? Right? Effective length is denoted by LE here. As you can see in this diagram, LE here or a small letter L. Okay. So it is denoted by LE or small letter L. Now this effective length of a column is that length. आपको यहाँ पर दिखाई दे रहा है L is equals to LE, मतलब ये जो लेंथ आपको यहाँ पर दिखाई दे रहा है this is the length of a column which has bent. इस पे bending आया है मतलब यहाँ पर buckling हो रहा है, right? तो effective length of a column is that length of a column which bends or deflects. Okay? तो जहाँ पर deflection and bending आते हैं उसको हम effective length of a column बोलते हैं. और effective length of a column depends upon the column end conditions. For example, अगर यहाँ पर pin end से, okay, अगर if it is pin end, effective length will be, इसका original length is L or effective length will be LE. Okay, if it is fixed and free ends, okay, effective length will be 2L. Similarly, it will depend upon the fixed end conditions, which we will see further in the other slides. Now slenderness ratio. So slenderness ratio is defined as the ratio between the effective length of a column and its minimum radius of gyration and is generally denoted by this symbol which is called as lambda. ये symbol को हम lambda बोलते हैं. So lambda is equals to ratio of effective length of the column divided by radius of gyration. Okay. So column and fixities. So column and fixities पे क्या आते हैं? the column end conditions पे, for example, some column will be fixed, some columns will be free at the end. Okay, so these are the column fixities. और यहाँ पर three major types है. One is hinged, second one is fixed, the third one is free end. Okay, so for the hinged one, you can see the diagram here. Hinged, this is a column, okay, and now hinged means an end is said to be hinged if it is allowed to move from its position. Now अभी इसका ये column का यहाँ पर position, if it was straight, अभी पहले straight हुआ होगा, अब यहाँ से it is allowed to move from its position. It is bending now, right? So it is now from its original position. It is allowed to move, okay, but not allowed to rotate in any direction. Okay, that is hinge and allows only rotation but does not allow translation. तो इस पे translation मतलब translate मतलब आपके column यहाँ पर है, यहाँ से उठा के दूसरी जगह पे लेके जाने के लिए. If you take it in this manner, that is known as a translation. Rotation means it is allowed to, अभी यहाँ पर पहले यहाँ पर straight था, now it is suddenly allowed to bend, so it is rotating in this manner, right? Getting straight and then again bending down, getting straight and bending down. So this is known as hinged end. Okay, so at hinged end, deflection is 0 but slope exists. Okay, deflection 0 honge but slope it will be there. Okay, so next we have fixed end. Now fixed end pe, you see the diagram here, this column, it is fixed from both the side. At the end, at both the side, it is fixed. So a column is said to be fixed if it is not allowed to move from its position as well as not allowed to rotate in any direction. So अभी ऐसा fix है तो it cannot move, right? It cannot rotate nor can it move. So if it is not allowed to move in both the directions, so that is known as a fixed column. So fixed does not allow both translation and rotation. So at fixed end, deflection and slope both are 0. Okay. Now free end. Generally this column, free end column, does not exist a lot, but free end means if the column is allowed to move in both the direction, that is if it is allowed to translate as well as rotate. अगर दोनों ही होगा वहाँ पर तो that is known as a free end. So at free end, deflection and slope दोनों ही होंगे. It will be present. Okay. So here you have a column end condition. So in column end condition, first condition is both ends are hinged. यहाँ पर दोनों end it is hinged. Okay. So if both the ends are hinged, original length of the column is L and its effective length will be again L only. Okay. So जो original length है वही length deflect भी होगा. So effective length is equals to its original length. So now both end fixed. In both end fixed पे, you see here it is fixed from here, it is fixed in here also. So उसका original length L रहेंगे और जो length जहाँ पर deflect होगा, it will be this much area will be getting deflected. So it is this much. This much area is getting deflected. Length of this column, so this much length is equals to effective length, which is equal to L by 2. Okay. Next we have one end fixed and other end hinged. So एक end hinged है यहाँ पर, other end यहाँ पर fixed है. ऐसे condition पे original length is L and जो length deflect होगा that will be equal to L by root 2. Okay. Similarly we have one end fixed and other end free. Original length is L. Here one end is fixed, the other end is free end. यहाँ पर it is free here. So it is free here. So for this kind of columns, the effective length will be equal to 2L. Now you see 2L is the position. It is this much area is getting deflected. So this much is 2L. Okay. Classifications of column. So the columns are basically divided into 3 types. The first one is short column, the second one is medium size column, and the third one is long column. Now let us see what do we understand by short column. Now, short columns are those columns. Okay, short columns are those columns where the failure occurs due to crushing. अब crushing की वजह से जो failure होते हैं column पे, so those columns are known as short column, and this crushing is due to direct compressive stress. Okay, short column do not buckle under the action of axial compressive load. अगर axial compressive load ऊपर से आ रहे हैं तो वैसे पे वो buckle नहीं होगा, मतलब it will not fail. Therefore, in designs of short column, buckling stresses are neglected and only direct stresses are taken into account. Because buckling से वो fail नहीं होते हैं, direct stress से वो fail होते हैं. That's why हम buckling जब हम short column design करते हैं तो buckling stresses हम neglect कर देते हैं और सिर्फ direct stresses लेते हैं. Okay. Now, medium-sized column are those columns in which the failure occurs due to both direct stress as well as buckling stress. Okay, and long columns are those columns where the failure occurs due to buckling only. Buckling की वजह से जो failure आते हैं उसको हम long column बोलते हैं. Okay, and slenderness ratio of such columns is very large. In design of long columns, direct stresses are neglected and only buckling stresses are taken into account. So डायरेक्ट स्ट्रेसेस की वजह से लॉन्ग कॉलम फेल नहीं होते हैं, इसलिए हम डायरेक्ट स्ट्रेसेस को नेग्लेक्ट कर देते हैं, एंड ओनली बिकॉज ऑफ बकलिंग स्ट्रेसेस लॉन्ग कॉलम फेल होते हैं. सो वी विल ओनली टेक बकलिंग स्ट्रेसेस व्हेन वी डिजाइन लॉन्ग कॉलम्स. So I hope this is clear. Now, if you try to understand according to the fixed end conditions, buckling कैसे होते हैं. So you see here, in the diagram, here we have a fixed end. If we let us first consider a short column. So let us consider a short column subjected to an axial compressive load using compressive testing machine. Okay. So if the load is gradually increased, it will crush under a certain critical load PC. अब हम यहाँ पर जो PC देख रहे हैं, this is a critical load. अगर हमने शॉर्ट कॉलम को कॉम्प्रेसिव टेस्टिंग मशीन के अंदर डाल दिया और वहाँ कॉम्प्रेसिव टेस्टिंग मशीन पे जो लोड्स लगते हैं, इट इज अ ग्रेजुअली अप्लाइड लोड, मतलब वो धीरे धीरे अप्लाई होते हैं. अगर वो ग्रेजुअली लोड अप्लाई करते करते जाते हैं तो एट सर्टेन लोड द शॉर्ट कॉलम विल क्रश, राइट. जहां पर क्रश होते हैं उसको हम क्रिटिकल लोड बोलते हैं, नहीं तो क्रशिंग लोड. ओके, सो दिस क्रशिंग लोड इज PC here. Okay, and now see here, the short column being short will not fail under the action of axial compressive load and will fail due to direct compressive load only. Okay, so हमें पहले से ही पता है short column direct compressive load से ही fail होते हैं. So the direct stress here will be equal to sigma C equals to PC by A. Sigma C here is direct stress, PC here is crushing load by area of the column. Okay. Now let us consider a long column of length L of the same material subjected to axial gradually increasing compressive load. At a certain load, the column starts bending, that is buckling or crippling. So if the load is increased further, the column will fail at a certain load P, which will be less than PC. Up long column के लिए, if you give the same type of load, compressive load, so after reaching a certain load, it will start bending, and this bending action is also known as buckling or crippling of a column, right? And as you keep on increasing this load, the column will fail at a certain load. और जहां पर long column fail होते हैं जो load के वजह से, that load will be less than this crushing load, which is crushing load was used for a short column. तो जो short column की column fail होते हैं उसका load ज्यादा होते हैं और long column का जो fail होते हैं वो कम होते हैं. Okay, so from here direct stress will be equal to P by A, bending stress M by Z. So maximum stress अगर long column के लिए find करना है तो it will be P by A plus M by Z. Similarly, minimum stress find करना है तो P by A minus M by Z. Okay, so I hope this is clear. Next, we have a case of a both and fixed. तो यहाँ पर figure number 1 पे as you can see it is a case of both and fixed. So for this, the buckling of the column depends upon its end condition, right? That we know. Now, a column with both end hinged will buckle as shown in this figure. यहाँ पर दोनों end hinged है तो it will buckle in this manner. Since both the ends of the column are hinged, deflection at A and B will be 0. But slope of tangent to the deflected curve at A and B is maximum. Slope will be maximum, deflection will be 0, right? So the vertical length of the column between the tangents having maximum slope is known as effective length. So the vertical length, which is this length, right? Which is in between the tangents having maximum slope is known as the effective length. So this LE here is the effective length. In short, the length over which the column buckles is known as the effective length. And if the column is hinged at both the ends, it buckles over the entire original length. अगर दोनों side पे hinged है तो ये over the entire length जो L था, originally length L था, over the entire length it will buckle. Okay, so hence in this case effective length of the column and the actual length is one and the same. Okay, so now let us consider a column with both ends fixed as shown in this figure number 2. Since ends A and B are fixed, slope at A and B is 0. यहाँ पर slope ही नहीं है at A and at B. There is no slope, and that is the tangent to the deflected curve at A and B will be vertical. Okay, the tangent at C and D. Now this tangent at C and D will have maximum slope. You see the slope here, QC, theta C and theta D. So here they will have a maximum slope. In this case, the vertical length C and D is taken as effective length. So this length C and D length is taken as the effective length. The column will buckle for the portion CD only. अब ये जो column buckle होते हैं वो portion CD पे ही buckle होगा. And the points C and D are known as points of contraflexure. Points of contraflexure. Now what is contraflexure? Contraflexure is the point where a bending moment will change its sign from positive to negative, right? तो जहाँ पर वो change होते हैं, it will become 0. 0 होकर जाते हैं, तो that 0 is known as a point of contraflexure. Okay, and since the tangent at C and D is maximum, it has a maximum slope. C and D can be treated as a hinged support also. अब यहाँ पर हम hinged support करके treat कर सकते हैं. In this case, the effective length of this column, effective length is equal to L by 2. Okay, so I hope this is clear. So next we have Euler's theory for long column. So assumptions made in Euler's theory for long column are as: Number 1, the compressive load is exactly axial. मतलब जो compressive load लग रहे हैं column पे वो axially वो बीच पे लगेंगे. Okay, axial मतलब right at its axis. Okay, right in the middle of the column. The material of the column is perfectly homogeneous and isotropic. The material with which the column is made, जो material column बना है, that is homogeneous. मतलब it is made out of the same material. Okay. The column is initially straight and uniform and of uniform lateral dimension. तो before जब भी कोई भी load नहीं लगते हैं, so initially it is जब कोई भी load नहीं आते, that time the column is straight and it is uniform. Okay, the column is long and fails due to buckling only. Now he is not considering short column or medium column. He is directly considering it for a long column. So he's saying long column long है and वो सिर्फ buckling से failure होते हैं. Shortening of the column due to direct compression is neglected. अब जो column अगर कॉम्प्रेसिव लोड पे आते हैं तो कॉम्प्रेशन से क्या होता है, लेंथ डिक्रीज हो जाते हैं. बट ही इज सेइंग दैट शॉर्टनिंग, कॉलम का लेंथ कम जो होते हैं बिकॉज ऑफ डायरेक्ट कॉम्प्रेशन, वो हम नेग्लेक्ट कर देते हैं. सो ही इज नेग्लेक्टिंग द effect of compression in this long column. Okay, the self weight of the column is neglected. और जो कॉलम का उनका खुद का वेट है उसको भी नेग्लेक्ट कर रहा है. The stresses do not exceed the limit of proportionality. अब जो stresses आते हैं कॉलम पे, that stresses will not exceed the limit of proportionality. Okay, so now here is Euler's formula. The buckling load for a long column of constant cross-sectional area and length L hinged at both ends and subjected to axial compressive load is given by equation this. So this is the main Euler's formula. Okay, P equals to pi square EI minimum by LE square. Okay, where P is Euler's buckling load, E is modulus of elasticity, I is moment of inertia, minimum moment of inertia, LE is effective length of the column. Now here limitation. अब Euler's formula का भी limitation है, मतलब we cannot use this again and again क्योंकि उसका limitation से, मतलब limitation is equal to failure. Okay, now crippling load by Euler's formula, as we know, is given by this formula here. And let us directly see. Okay, now Euler's crippling load sigma c is given by P by A. Okay, where P is equal to this value here by A. Okay, now the value of sigma c thus depends upon E and the slenderness ratio LE by K minimum. Okay, जो value of sigma c क्या है? It is the crippling stress of Euler's crippling stress, and it will depend upon value of E, Young's modulus, and slenderness ratio LE by K minimum. Okay, so the column material cannot withstand compressive stress more than the yield stress for the material. For mild steel yield stress, mild steel के लिए yield stress capacity जो mild steel लेते उसका yield stress is equal to 320 Newton per mm square. Young's modulus is this much. And now maximum value of sigma c will be equal to this much only, because इससे ज़्यादा लिया तो it will go out of the limit of proportionality. Okay, so here sigma c will be more than or equal to 320, and sigma c is equal to this value here, will be less than or equal to 320. Now from here at the end we get this value here. So the meaning of this value 80.48 means that thus for the Euler's formula to be valid, Euler's formula जो है उसको valid होने के लिए the slenderness ratio for mild steel column should be greater than or equal to 80.48. अगर Euler's formula हम use कर रहे हैं और if we want it to be valid, तो slenderness ratio जो है, this is the slenderness ratio, should be greater than, slenderness ratio should be more than 80.48 or it should be equal to 80.48. अगर इतना नहीं है तो हम Euler's formula use कर नहीं सकते, it will not be valid. Okay, so Euler's formula cannot be applied if the slenderness ratio for mild steel column is less than 80.48. अगर 80.48 से कम आया तो we cannot use the Euler's formula. This is the limitation of Euler's formula. Okay, so this is the main limitation of Euler's formula. Now next we have factor of safety. So Euler's formula gives the buckling load at failure. To determine the safe working load, a suitable factor of safety must be applied. So generally factor of safety for mild steel is taken as 3 and for cast iron it is taken as 5. Now next we have safe load. Safe load is nothing but it is the ratio of buckling load by factor of safety. जो buckling load column का आता है और जो factor of safety हम लेते हैं that will be safe load. Okay. Now let us see what do you understand by strength of column. Strength of column means that the load carrying capacity of a column. मतलब column कितना load ले सकते हैं. Okay. तो strength of the column is given by Euler's formula. जो Euler's formula है, it is given by this formula, and the strength of column depends upon the slenderness ratio. Again, फिर से जो strength of the column है, again it is depending on slenderness ratio. Okay, so okay, जब slenderness ratio increase होगा, उस time पे compressive strength of the column decreases. The strength of the column also depends upon column and conditions. Okay, column and conditions मतलब अगर वो fixed है या free है या hinged है, it will also depend on those conditions. Now we have next Rankine's formula. Now Rankine suggested that following empirical formula for calculating strength of a column. So this is the formula that he has given, where PR is the Rankine's crippling load, PC is the crippling load, right? This is the crippling load, and PE is the Euler's crippling load. Okay, तो अगर हमने PC को सिग्मा इंटू C से हमने रिप्लेस किया और PE को पाई स्क्वायर बाई EI से रिप्लेस किया, यहाँ पर it has been replaced here and यहाँ पर भी रिप्लेस किया है, तो इसके बाद if you add all of this, finally you will get this. So this is the Rankine's formula. This is the Rankine's formula. Let's see in the next slide here. So this is what you will get. Now from here, A, in the last numerical you see यहाँ पर A, this A is equals to sigma C by pi square E. Now this one here is the final Rankine's formula, which we will be using to find to do the numerical. So PR here is Rankine's formula, sigma C is ultimate crushing stress, A is the area, and small a here is Rankine's constant, LA is effective length, K is minimum radius of gyration, and I minimum is minimum moment of inertia. Okay, so here these are the table. Now to take the value of sigma C and FC, अगर mild steel है तो it will be 320, और A का value, this A here is the Rankine's constant, will be equal to 1/7500. Cast iron है तो it will be this much, and A का value Rankine's constant will be this much. If it is a timber, it will be 1/750. Okay, so this is it. You just need to understand this table. So this is the end of the slide, and I hope this explanation is clear. It is very simple and basic, and from the next session onwards we'll be solving numericals. Okay, so I'll see you in next session.